Alright, let's answer that question, why we use AC current. It's a topic called electromagnetic induction. Oersted discovered that a steady current produced a steady magnetic field around a conductor, and we used our right-hand rule for that to determine those directions. It is logical, therefore, to assume that a steady magnetic field around a conductor produces a steady current, but this is not what happens. Faraday performed 3 different experiments. He moved a wire through a horseshoe magnet, which looks like this, north, south. He had a wire, here it is here, here it is. When he was bringing the wire in, current would start to flow in it, but as soon as it got there and he stopped moving it, the current in the wire stopped. If he had a coil, and he took a bar magnet and he put the bar magnet into the coil, and current started to flow in the coil until he stopped moving the bar magnet, and then it would stop. And then he took the iron core of a coil with a bar magnet, and then he removed it, touching the core. But as long as things were changing, he was getting current. So there were 3 things here. There was current, there was the magnetic field, and there was movement, or we might even say change, or necessary. All of these situations produced a current in the conductor, but only when something was moving or some change was taking place. As soon as everything became steady and constant, current immediately stopped flowing. This was turned into Faraday's law of electromagnetic induction. An electric current is induced in a conductor whenever the magnetic field in the region of the conductor changes. So I need this magnetic field to change. I can get more current if I move the wires more quickly or if I use stronger magnets. So then he came up with this setup here, which is pretty impressive. Okay? I've got a wire current, a circuit with a battery and a switch. This part of the circuit is wrapped around this iron ring, not necessarily touching the iron ring, just wrapping around it. And the same thing here, wrapped around it. A galvanometer measures current. This thing measures very small currents. So what he did was when he turned this on, the current goes from 0 up to some value very quickly, yes, and then becomes constant because this is DC current being made. So when he closes it, current starts to flow here, and the current starts to flow here. It makes a magnetic field around these wires. The iron ring transfers that magnetic field over to here, and that magnetic field, as it's changing right in this area right here, as it's going from 0 up to some value, the magnetic field here makes current flow over here. So by closing this circuit here, he made current over here, but only for an instant, because as soon as the current became steady, current stopped flowing over here, because that's Faraday's law up above here, is that I need the magnetic field to be changing, or I need some sort of change. So closes it, current flows, magnetic field made, magnetic field over here, makes current flow here. But only when it's open or closed, yes? Faraday noticed deflections of the galvanometer meeting when the connection between the first coil and the battery was made or broken. No current flowed in the second coil when a large steady current flowed in the first. So only when this was opening and closing, he seemed to be getting what he wanted here. So I guess you could hire somebody to open, close, open, close, open, close, open, close, open, close, open, close, open, close. That would, I seem to, would solve our problem, except that seems to be very impractical to have somebody's job to sit here and open and close it and open and close it. If he wanted to keep current flowing in the second circuit, you need current in this circuit to always be changing. which would make the magnetic field in the ring always changing, which would always be making current over here. Magically, for the record, there's no battery over here, yet I'm getting current to flow. So that's why they made a switch to AC current. So if instead I'm using AC current over here, let's pretend, the current over here is always changing, never constant, right? Remember our graph of AC current looks like this. Yes, sometimes it's going in one direction, sometimes it's going in the other direction. The current over here is always changing, therefore the magnetic field in the ring would always be changing, which means I would always be making current in this secondary coil. And so that is why we use AC current, because it magically allows us to make current flow in this second circuit. And how we use this idea will be a topic for another time, but this is the reason why we use AC current. It's because I can generate a different type of I can generate current in a completely separate circuit by using it. We call these things transformers. They are the large green boxes that you might see around the neighborhood. There's one in between the senior school and the junior school. There's a great big transformer that you walk by. And that ends our look at induction.